bienvenidos a esta clase. Básicamente estamos desde Estados Unidos compartiendo con ustedes un tema muy interesante que tiene que ver con las redes multiplexadas. Robert nos va a colaborar con una explicación de más muy interesante en el sistema. Y básicamente estamos acá en el Hudson Valley tratando de llevar a cabo un entrenamiento en conjunto con Robert que tiene que ver con el trabajo de autos
Claro.
híbridos y eléctricos. ¿Ok? Entonces, bienvenidos a la charla. Robert es una persona experta en electromovilidad, es experto en sistemas automotrices, experto en todo tipo de mecanismos de operación y en autos. Y bueno, toda su experiencia pues nos la va a transmitir acá en un ratito. He logrado sacar a Robert de su entorno, digamos, de trabajo y nos va a explicar un tema. De manera ordenada, ustedes van haciendo las preguntas, yo voy buscando la manera de compartirlas con él del tema que estamos viendo, por favor, porque no es fácil, pues, contestar todas al mismo tiempo. Entonces, si tienen alguna pregunta por ahí, la esperan el momento y la van realizando. Y nada, espero que sea de su agrado. Como siempre es un esfuerzo que hacemos para que todas estas cosas salgan bien. Estamos en un lugar de primera, o sea que estamos disfrutando muchísimo el tema del compartir información. Desde Latinoamérica estamos compartiendo información acá. Tenemos gente que está, bueno, ya creo que está la mayoría, ya igual ya cierro la sala porque ya están demasiados. Entonces hay gente de Colombia. Robert, we have people from Colombia, from Argentina, from Venezuela, from Guatemala, from Mexico,
Wow.
from Ecuador, from Peru, from Bolivia, from Canada, from USA. Wow, from Robert.
Wow.
Yeah. Ok, compañeros, entonces yo le voy a dar la bienvenida a Robert y por favor, de manera ordenada, el tema de las preguntas, porque bueno, doble trabajito aquí para hacerlo. Y les pido el favor sugerido para aprovechar a Robert al 100% del micrófono, de tenerlo ahí siempre, eh, nada, de estar atento con el micrófono. Aquí está clase de Robert y bueno, la van a disfrutar. Welcome, Robert. Thank
Thank you.
you for this space. We will enjoy.
Perfect. Thank you for having me. This is exciting.
Perfect. All
Uh,
right. So good afternoon. We're going to spend a little bit of time today. We're going to talk about CAN bus systems in automobiles. That's the main communication system that most all cars use now, controller area network. Um, it was designed way back it was actually designed in the 80s. It was put in the first car in Mercedes-Benz in 1991. Um, it uses a chip, a processor inside of a control module, a CAN transceiver to transmit and receive messages, right? So this is a clocked system. It has to work in a certain amount of time. The messages are expected to have certain changes in amount of time. It is a differential bus. In other words, we're going to use the total of the two switched voltages. We'll talk more about that to determine when a message is broadcast. Typically, they're two-wire systems. If you're familiar with older cars, older Fords, SCP, GM single-wire bus, the messaging is similar, except for all CAN buses are going to be two-wire. And CAN bus across the board is going to use a message type system that is similar across all manufacturers. So even Chrysler, Ford, GM, Toyota, Honda, if it's talking in CAN messages, it's going to be very similar how the message is designed across the manufacturers. Pretty fast. We can get speeds up to 500,000 bytes per second. That's really fast considering we used to be like 10,000 bytes per second when we had UART. It's up to 500,000 bytes per second now. Much faster than that with the next generation FCAN and FlexRay. It can be different speeds. We can have multiple speed buses on a vehicle. We can have a high speed CAN. We can have a medium speed CAN, low speed CAN. All of that, depending on how important the messages are. Obviously, the more messages we send over a bus, the more tied up the bus gets, and it gets difficult to send more information. So The different higher speeds allow us to transmit messages that are much more important that need to be transmitted at high speeds, such as airbag messages, engine control, electric vehicle controls, things like that. A low speed bus might take something along the windows like a window control or a turn signal command, something like that, that doesn't need to be a real high speed. Some manufacturers have changed the name of the CAN, but it's still CAN. For example, General Motors calls theirs GM LAN, which is GM Local Area Network, but it's still a CAN. It's still a CAN design, still uses CAN transceivers, two-wire bus, same wiring architecture. They just chose not to call it CAN. They wanted to call it their own system, so they call it GM LAN. Again, it's used by pretty much every manufacturer out on the road now for almost all of the messages. So today we're going to talk about how the messages are designed, some of the architecture in the system of how the system is designed, and how we can do some fault tracing. So the messages are similar to a J1850, which is our old SCP bus. It is a voltage differential bus. It is a 2.5 volt recessive. So when I say recessive, I mean there's nothing happening. No messages are being broadcast. It is at idle. When it is at idle, you will have 2.5 to 2.6 volts as its bias voltage. Normal voltage, 2.5 to 2.6. No communication is occurring. The reason they make that 2.5, 2.6 volts and not 0 is because way down on 0 on ground, that's where all the rest of the car grounds. So things like the alternator, blower motors, window motors, they all use a dead set zero ground. So if there's any noise, electrical noise on the ground, it would interrupt the bus if it was brought right to ground. So to prevent that interference from other items in the vehicle, we give it a bias voltage of 2.5 volts. If you're familiar with oxygen sensors, a lot of newer oxygen sensors give a bias voltage off of 0 just so that it doesn't get interfered with other items on the vehicle that ground to chassis ground. Okay, so 2.5, 2.6 volts, that's CAN high and CAN low are our two signals that will come out of the computer. CAN high is a voltage that rises above 2.5 to talk. CAN low is a voltage that falls below 2.5 volts to talk. Each one will increase or decrease its voltage by 1 volt. So in other words, CAN high, to make a bit, which is one piece of information, a bit will go from 2.5 volts to 3.5 volts. CAN low will go from 2.5 volts down to 1.5 volts. This happens in unison. It's not that the 2.5 volts goes up to 3.5 and then maybe the 2.5 goes down to 1.5. It happens in unison. As the CAN high talks, 2.5 goes to 3.5, 2.5 low goes to 1.5. We've just created a message. It's important that we understand that. These messages, the CAN high switch from 2.5 volts to 3.5 volts and 2.5 to 1.5 volts has to happen in unison. It's because the voltage that the computer sees is not that single switch of CAN high from 2.5 to 3.5 or the single switch of the CAN low from 2.5 to 1.5. It sees the difference of the switch for both. So if you think about it, CAN low is a 1 volt change from 2.5 to 1.5. CAN high is a 1 volt change from 2.5 to 3.5. If the computer was to measure both of those voltages and it saw one go up 1 volt and one go down 1 volt, how many volts is the computer going to see on that line? 2. It's not going to see the single 1 volt change or a single volt change. It's going to add them two together. It's a voltage differential circuit. It sees a difference and change. 2.5 3.5, 1.5. That equals 2 volts from 3.5 to 1.5. So the 2-volt change that occurs when the transceiver inside the module begins to broadcast messages is what creates that voltage change and makes a message. So it's actually the switching of the 2 volts on the CAN bus line. So I started to mention some of the message components. We have what's called bits and bytes. Bits are one, think of them as one letter in the alphabet. Think of a byte as a word. So if we were to take a bit and take 8 bits and put them together, we just made a byte. So 8 bits equals 1 byte. 1 byte you can consider as being a word. If we put a whole bunch of bytes together, we just made a sentence. So by creating bits, which are letters, we begin to build a message. So we build a bit. 1 bit, 8 bits becomes 1 byte. It's important to understand that because that's what the computer looks for, is that converts into a byte and begins to make a message. So we talk about bits and bytes. We're up to 500,000 bytes per second. Speed-wise, if you think about that, that's pretty fast. That means that this module, all modules on the CAN bus, have the ability to make a 2-volt transition 500,000 times per second. So it can go from a bias voltage to this 2-volt change 500,000 times a second. That's pretty fast. So what this starts to look like when we create a message, I have on the screen. So we have a message construction, and each CAN bus message has a similar construction. Doesn't matter if it's a GM, a Ford, a Honda, Chrysler. If that message is being transmitted and received from a module, they're all going to have the same functions. Just when they switch on and off is what creates the message. So they all have the same functions. The first thing that happens in the message is a single bit. It is a start of frame message. That just means, hey, pay attention, I'm going to start talking. A lot of times when we see a start of frame message on a scope pattern, you might see that voltage a little higher than the 3.5 or a little lower than the 2.5. The reason for that is that grabs the computer's attention that, hey, this is a new message, pay attention to me. After that, we're going to give the message some ID parameters, ID 10, 9, 8, and 7. That gives that message an indicator as to who it's coming from, right? So if the airbag module is sending out a message, the ID of the airbag module will fit into ID 10, 9, 8, and 7, gives it an idea who that message is coming from. We put a stuff bit in there then. A stuff bit is a bit that only that module knows what's going to be transmitted, and the module that's receiving that message will understand that stuff bit. If the stuff bit does not match for that module, that message is considered no good. So if it starts to broadcast a message, it starts to start a frame. It starts an ID 10987, says, hey, I'm the airbag control module that's starting to talk, and the stuff bit is not correct in that frame. In the next frame, all of the modules go, this message is bogus, we're not going to pay attention to it. If the stuff bit does happen to match, we're going to go through with the rest of the IDs. We're going to say, hey, here I am the airbag control module, I need to broadcast the message. We're going to go into the control. Again, this is another, hey, look at me, make sure my message makes sense type control. This is the language the computer's speaking in. These can vary depending on the module, how many bits we're going to fit into each area there. And the next thing is what's important, right? That's our data. That's what it's trying to say. So we have these frames of data, these bits of data right here that's in red on my screen. Again, we have the gray stuff bit, but the red is the actual data. And if you look at the data here and you see where the zeros are lined up with this, with my CAN bus message voltage that's been recorded on a lab scope, you'll see that this is at a recessive state, which is 2.5 volts. This, even though nothing is changing in this area here for the data, right here, nothing is changing in the data. That does not mean that the module is not actually sending out data. It's sending out 4 bits of data right now that's saying recessive, off, 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 off. Off, 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 0, 0, 0, 0 will indicate 4 bits. That's part of our message. If we were to go off, on, we still have 4 bits, but we have 2 that are recessive, which are off, 2 that are on, which are become dominant. Just because it's not changing in this area does not mean that that module isn't broadcasting a message. This data from 7 to 4, 3 right here, 7 to 3 right here, is all zeros. It's not changing voltage. It's staying at a recessive 2.5 volts. That's okay. It just hasn't broadcast any information yet. The next thing that happens is we put another stuff bit in there. If that bit does not match either recessive or dominant, again, all the other modules that are looking at this message are going to go, hey, I don't need this message. It's garbled. I can't use it. Go back and try again. It's just a check bit. We have 2 more. Our data of 2 and 1 is also located right here. That is also down at 0. So this message from this module at this point in time is 7 bits from 7 to 1 of a recessive bit, which is off, 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 off. So we have 7 zeros. 0, 0, 0, 0, 0, 0, 0. If we were to take those 7 zeros and put them into a hexadecimal chart, we can convert those 7 zeros into a hexadecimal component. At the final bit, data 0, we came on. So that data 0, we turned on, we became dominant. It rose above its bias voltage. So we went from off, 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 on. So that message is 0, 0, 0, 0, 0, 0, 0, 1. Whatever the coding is built in the computer that comes out to be 0, 0, 0, 0, 0, 0, 1 is the data that module is actually transmitting. It could be anything from where to put the speedometer needle. It could be anything from where the accelerator pedal is. Any data bit that you can put in there is stuffed into our data area. That's what's important. Our cyclic redundancy counters, CRCs, these are put in there as an addition to the message, and they're also put in there to make sure that the message is cyclic, right? So that it's cycled correctly and that the modules can understand that message. At the end of the cyclic redundancy counter, we have a delimiter. The delimiter is an indicator that I've made up. I've talked my startup frame. I've done my arbitration, my control, my data, my cyclic redundancy counter. Now my delimiter is here, and I am done with this message. The next thing we're going to move on to is ACK. ACK is acknowledge. So what the ACK is designed to do is for the message to be acknowledged by another module. If we look at how a CAN bus is wired, all of the modules can technically talk to one another. So if I look at the airbag control module, that can talk to the radio. But the message that I'm trying to send may not need to go to the radio. that message that I'm sending from the airbag controller might be meant for the body control module. Because it goes to all modules, I need the body control module to be the one to say, hey, I got your message. I'm going to let you know I received your message. And then when you see that I understood your message, you can stop broadcasting. So the airbag control module will send out a message, whichever module. It wants to make it to another module. The BCM receives the message that it was supposed to get. The acknowledge in here delimiter is going to change. The acknowledge delimiter must be a recessive 1. The ACK slot transmits a recessive 1. So like I said, a recessive 1 would be an off bit of 1. So recessive is our bias voltage, our dominant is talking. If we have a recessive 1, that means that we're looking at a 1 bit that has not talked. So the non-communication, a 0, is a 1. So that 1 in the, excuse me, the ACK slot, the module transmits a recessive 1. So whatever module made this message transmits a recessive 1. When the module receives this message that needed to see it, for example, the airbag sent it, BCM needs to see it. The BCM changes that 1 to a 0. That way, airbag says, oh, you got my message. I can stop talking.
Okay, Kenny. Amazing. I have two questions
Yes.
from people. One question. Okay, I'm going to mute use. All right. The control area, okay, is different for each module. Okay.
Yes.
Yes, it's okay.
Yes.
Yeah, for example, for the ECM, it's different from BCM or TCM.
Yes.
It's okay.
The actual bits will be different in the control area.
Mute.
So the actual bits will be different in the control area where we do this switching, whether we are going to be a 0, 1, 0, 0, or 1 in the control area. But the thing that won't change is the control will remain at 1, 2, 3, 4, 5, 6, 7 bits of data.
So if we look here, 1, 2, 3, 4, 5, 6, 7 bits makes up our control area. That's going to stay the same. What we do with those bits in that control area is going to change from module to module.
Other question? I have, okay, mute, just mute. Okay. Other question. In the data area, what happens if, for example, for the VCM turn off, fuse control ground, if the VCM lost, for example, the ground or power supplier, what happened in the CRC or what happened in the data?
Okay.
Would you be considering the BCM as the module receiving the data or sending it?
Receiving.
So receiving. So where it is receiving, CRC won't really change. That's sent from the other module. That's a cyclic redundancy. What's going to change is that because the BCM could not receive that message, it can't change that acknowledge slot from a 1 to a 0. So if the airbag sent out the message and it went to the body control module, body control module's offline because the fuse is blown or the ground is gone, it doesn't have the ability to change that acknowledge from a 1 to a 0. If it doesn't change that from a 1 to a 0, the airbag module will continue to repeat that message. This becomes a problem. I was going to bring this up later. Here. If you look at this message that I have on the screen here, it is a repetitive message. It's the same message here as it is here. It's just repeating over and over again. What is happening is a module is putting out a message on the bus going, hey, airbag to BCM, BCM, this is my message. The BCM doesn't change that acknowledge slot because it's offline. So the airbag hops back on the bus and goes, no, here's my message. I need you to understand it. Airbag sends it out. Body control cannot change that acknowledge slot. It keeps repeating that message. This becomes a problem because it will tie up the bus and nobody else can talk.
Thank you.
No more questions?
No more questions.
Okay, good. So again, that acknowledge slot, that's an important one. One of the failures that I typically see this is a big red flag to me in diagnosis. If I see a module repeating, if I look on the bus and scope my CAN bus and I see the same message repeated several times over and over and over and over and over again, that to me is a big red flag that I have a module that's offline. Right? It can't take and change that acknowledge slot from a 1 to a 0. So it can't receive it. Whether the fuse is blown in that module that's receiving it, or the ground is missing, or it's just failed internally, or the CAN bus wiring is damaged going to that module. Something is wrong. So in diagnosis, I would look at this message and go, oh, I know I need to diagnose a module that's offline. I don't necessarily have a wiring problem right here because I have good messages. Somebody's just not accepting the signal and returning it back. We have another slot in the ID bits that's called arbitration. So with so many modules on the CAN bus, like we started to talk about earlier, some of them are more important than others, right? If you're just driving down the road and nothing is happening and you're just cruising down the road, you might need the engine to talk to the transmission just to get some information from the transmission, but nothing important needs to happen. But if you apply the brakes, the car starts to go into a slide, the anti-lock brakes start to work, and we need to reduce the throttle to prevent the car from sliding, the engine control module would need to receive a message from the brake control module that says, hey, the wheels are locked up, you need to reduce the throttle. That message from the ABS to the engine control module needs to be more important than the engine control module to the transmission talking about vehicle speed. So we have to have a way in there for the modules to take arbitration. Arbitration is, hey, I'm more important right now. I need to speak. You need to stop tying up the bus. So we give them some importance in this arbitration frames that says, hey, I'm very important right now. You need to stop talking. For example, the car is going to hit a tree and the airbag is going to send off a message to send off the airbags. Everybody else on the bus needs to stop talking so that the airbag module message can get to the other modules as quickly as possible. So we give that module an ID point right here that says, hey, I'm important. You guys need to stop talking. I get arbitration over you. It handles the initial call. So it's going to decide which message is most important. Sometimes these messages will time out. Other times they can completely tie up a bus and communicate any other communication from occurring. So how this works, if you look at what I have on the screen here, node 15, if we're not familiar, a node is a module. That's just computer lingo for a module. So node 15 would be a module. We'll call this one right here. We'll call this one a engine control module. We'll call node 16 a body control module. When we change this slot right here from a 1 to a 0 in node 16 understands that I got to stop talking. Node 15 is way more important than I am right now. I need to let that module continue to talk. So node 16 receives a 1 bit and ID bit 4 and says, I need to stop talking. You're more important. That's how I get arbitration, is through the ID bits. Okay.
Okay, we have a question.
Okay.
How can I to know who is the master module?
How can you know who the messenger module is?
Yeah.
So
There's several ways we can know that. What they're going to tell us, how we're going to know where it's coming from, is this ID and arbitration right here, the first set of bits. How do we know as technicians? The best way to know right now is to use Picoscope 7. Picoscope 7 has a CAN bus decoder that you can use a decoder and it'll tell us what module is talking.
What is best tools you have for working decoding?
for right now for decoding, the best tool I have
Yes.
is the Picoscope 7. I'm sure you have something better than that.
It's so expensive.
It is expensive.
Yeah.
Okay. So that's how our messages are built. That's our frames, and that's how we get this message broadcast. Now, this is CAN. CAN says we're going to have this many bits in arbitration, this many bits in control, this many bits in data, this many bits in CRC, this many bits in acknowledge, and then our end of frame. I'm not going to speak much about it today. It's a whole nother class, but what I want to talk about real quick is just FCAN. FCAN is a flexible CAN that says, okay, you're no longer limited to this many bits in this area. So if I have more data I need to broadcast, flexible CAN can send out an indicator from that module that I need more bits and data, so my data is going to have more bits in it. I can make that area larger with flexible CAN. Okay, so that's how the CAN bus messages are built. I want to talk a little bit about the architecture so we can look at how they're diagnosed. Here. Get to the right slide here. So we typically have a couple different ways of building these networks. We can build them with either a star bus configuration or a pass-through configuration, which would be called the ring, or a combination of both, right? So we can have a star communication layer, which would be where each module branches off of a separate communication bus. And each module would receive a message, but not each module has to broadcast every message it receives. We can have a ring style, which would be where every module has to bypass that message. So if I want to get a message to this module down here, it has to go through a module over here. And then we can have a combination of ring star, where we might put some modules in parallel to the ring network. So a ring network would be similar to a series type circuit, and a star network would be similar to a parallel type electrical circuit. If we combine the two, a series parallel, we get a ring star network. Chrysler, for example, uses a star network right there. So they use a common connection point for each module to receive data, and they use a common connection point. On a Chrysler product, Dodge, Jeep, these connection points, we call them star connectors. If you're in the field at all and you've diagnosed any CAN bus faults on those types of vehicles, I am sure you have replaced a star connector. They're extremely high failure points.
Star connector, do you remember Star connector in old system GM?
an old single wire.
Single wire. Okay.
Single wire, they had it in class 2 data. And some of the GM still now GM low-speed LAN, and some of them is still a single wire. Even they
Okay.
call it local area network.
Okay, the new system GM LAN with single wire is similar to all class
Class
2.
2,
Oh,
same.
Only
Only
difference
difference
is
is voltage. It's 0 to 5 volts on the GM low-speed LAN, where Class 2 was 0 to 7 volts.
I remember 0 to 8, maybe 0 to 12. When
Yeah.
you use the scan tools or BD2.
yes.
Yes. Is it okay?
So GM called it 0 to 7, but it was actually like 7.8 volts. So it was 0 to 8 volts. 0 to 12 was before that. That was UART. UART was 0 to 12. The problem with using 0 to 12 volts is if there's any noise on either end of that, area at ground or at the 12, it's going to screw up the message.
Yes, in this time we used the Touch 2. I had a function was ping to module in class 2 testing.
Yes.
Do you remember?
Yes.
Okay.
I actually enjoy testing Class 2 because it's easy. And that goes back to Chrysler. I enjoy testing Chrysler CAN bus faults because it's pretty easy. If I think I have a module that's bad, that's bringing down the whole bus, that's, shorting out a whole bus or something like that and ruining my messages, I can locate this central star connector and unplug that module from that bus. If the rest of the communication comes back now, I know that that's the module that has the fault.
Okay, but in this time, the GM Class 2 was the fastest speed in
Yes.
the chair.
Yes. It was the fastest at the time.
Yes, it was at all
100
times.
Yeah, 125 maybe
Yes.
kilobits per second. Now we're up to 5. We're almost.
We're almost one.
Beautiful times.
Yeah, it was. It was easy.
The-
It was very good.
It was very. There's very few problems with Class 2 data. It worked well. Just wasn't fast. So we'll go back to the Chrysler Star connectors. Here's a picture of one. This is that point where all of the modules are joined together. So we just join all those modules together on a Chrysler vehicle. These are fairly accessible on almost all of them. They will call them like instrument IC star connector, so instrument cluster star connector. If you're looking for an IC star connector, it's going to be near the instrument cluster. If you're looking for an IP, it's going to usually be near the panel. It's usually on the passenger side. On the Chryslers, very small pins, contact problems. We have in a CAN bus system what's called terminating resistors. The terminating resistors are built into this star connector on these, and that's where the fault is. The solder joints go bad on those resistors and begin to cause issues. Talking about Class 2, there's a Class 2 picture right there. The star connector, you could remove it and take all the buses off the line.
I can remember you have two connectors, front and rear.
Yes.
Yes.
Yeah, one in the trunk usually, or somewhere for all the modules in the back, and one up here somewhere by the firewall.
In the water in the rear, it was fouled. I can remember serial control module, airbag control module, TCM control module. Yeah.
Yeah, they were all tied together, and that little comb right there tied everything, all those modules together.
Okay, but in the new system of GM, you still have a connector, a star connector.
It still uses a star connector.
In the one wire. Okay.
The GM low speed LAN, they still use this architecture right here, where they will use a single wire. And they still use it. They still use a point you can disconnect. It's fantastic for testing.
Yeah, it's a green cable.
Yeah,
green cable.
Yes.
Light green or green dark, but green.
Yes.
In the terminal number 1 of DLC.
Terminal 1 of DLC goes to that. So you can take And it's exactly right. You're looking at this picture here. If you look at this terminal right here, that's the one that connects to the DLC, goes to terminal 1. If I can't talk on this bus, I can jump this terminal from my DLC to each one of these modules individually after removing that connector to see if I get communication back.
This is the star topology.
Star topology is similar to the new GM. We'll get to that right. There you go. Star topology right here. This is where each module has to have the messages pass through it. So if you look at this up here, if this module right here, the beginning module right here, wanted to send a message to this module down here, that message has to go through this one, this one, this one, and this one. The concern with that is each one of these modules receives that message. It has to read the message. When it realizes it is not for it, it does not change that acknowledge bit, so it allows it to continue on down the bus. If that message comes from here, 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 and this module happened to change that acknowledge bit from a 1 to a 0, it wouldn't go any further. It would never make it to the module down here that it needed to get to. So to speed that up, they don't allow any module to change that acknowledge bit unless it's the one that needs that message. So this module would send out a message. If it needed to get here, it would go here. The acknowledge would stay 1, acknowledge would stay 1, acknowledge would stay 1, and it got to this module right here, that acknowledge bit would go to 0. That would indicate to this module that originated that message, I got what you wanted. But this is a slower system because every module has to read that message, decide whether it is for that or not, or just let it pass through. When you have the star system, it can be quicker to send, everybody gets the message at the same time. So that's the advantage. In this system here, if we break this system in the middle, we'll lose communication with half of the modules. Where the star is, if we broke the connection at a star connection, we would only lose connection with that module. We wouldn't lose it with them all. So if we broke a connection here, we're only going to lose connection with this module. In this type bus, the ring type, you break this wiring here, we're going to lose connection between these modules.
Okay, I have a question for participants. What is the network more used in EV vehicles or hybrid vehicles?
Which one gets used the most?
Yes.
So for our drivetrain components and that, it is still CAN. Where we have started to change to FlexRay and Ethernet is most of the ADAS components. Things that need to be really fast, cameras, radars, things like that.
What do you think will be a feature of a network?
When?
Yes.
When will they change to getting rid of CAN?
Yes.
Soon. And the reason I say that is SAE has determined that we're going to go to UDS pretty soon. So UDS will be a new connection. It'll be a different DLC. It is FlexRay and CAN. And you're talking 1 million bytes per second.
What brand has a FlexCAN here or FlexRay?
FlexRay?
Yes.
Our 2019 Bolt has it. So everybody uses it, mostly for collision ADAS stuff. BMW, Mercedes-Benz, European cars will use it for all the control modules, all the engine controls, transmissions, anything that's really high speed.
Drivetrain.
Yeah, drivetrain. In the United States, some manufacturers have started switching to FlexRay for drivetrain, but it's not widespread yet.
In infotainment?
Infotainment. Infotainment is typically Ethernet. Yeah, very short distance runs. Cheap. That's a cheap network. Honestly, Ethernet is cheaper to build, and the components are cheaper, and it's much faster than CAN. So why manufacturers didn't just do that off the right off the get-go, I don't know.
Okay. Actually, optical fiber we don't have in some cars.
Correct.
Yes.
Yeah, they can even do Ethernet that's not fiber optic. It can be Ethernet that's, hardwired, even still with copper wires. It's just, wired like your Ethernet in a typical computer. Typically only 2 terminals though. It's not multiple. So back to CAN. We're going to talk, we got 10 minutes or so left. I just want to take a couple minutes and talk to you real quick about some diagnosis. The first step, I'm not a big guy to check resistance in anything. I don't believe really much in resistance testing. I'd rather measure current and voltage. But the first test I do when I get a module that doesn't talk is a resistance test. Because if you look at this system here, my very first module right here has 2 resistors, 60 ohms and 60 ohms, that are in series that will add up to 120 ohms. Same thing back here, right? So this one and this one will add up to 120. This one and this one add up to 120. 60. Right? So 60 and 60 give me 120 total. But if you look at the way this is wired, when you take these 220 ohms put together, they're in parallel. If we understand our basic fundamentals of electricity, 220 ohm resistors in parallel gives us a total circuit resistance of 60 ohms. So the only way that this whole circuit could have 60 ohms is if the whole thing is connected from here to here. So if I take my meter and go in here and measure this pin 6 to 14, which is my CAN bus high speed, 6 to 14 right here, that's going to measure this whole circuit from here to here. I should see 60 ohms. If I see 120 ohms, I have a break between here and between the end and where I'm starting at. If I see 0 ohms, CAN bus high and CAN bus low are shorted together. If I see something between 60 and 120, I have high resistance somewhere else in the circuit. In series. The one thing people forget that we talked about this morning is when I check resistance from 6 to 14 on a bus without a gateway module, I expect to see 60 ohms. The next test we need to do, we need to check pin 6 to chassis ground and pin 14 to chassis ground to make sure neither one of those CAN bus wires are shorted to chassis ground. So that's in a system without a gateway. If you look at this system that has a gateway in it, this is a Ford. This is actually our Mach-E. We have a gateway module here that decides all of the data, who gets to talk to what. There is no physical connection in this module for the scan tool or your meter to get directly tied into the bus for, excuse me, for that to get right on the bus, because it goes through the gateway first. So there's no more physical connection from the control mod, from the DLC pin 6 and 14 to the bus. So we have to find some place in the system where we can tap into the bus to measure that CAN bus resistance. One of the questions I get is where's the best place to tap in? And that always depends on the car and how easy the modules are to get at. Find the easiest one to get at and tap into that module somewhere and try and test it. For example, this bus right here has no connection to the DLC, but it's still, you can still talk to these modules with a scan tool but they're not hardwired to the DLC. So you need to test the resistance in this. We need to find where this wiring is somewhere and tap into it and measure the resistance at a module or at a connection somewhere to look for that 60 ohms. Briefly, we talked quickly. I just want to bring up one point. If the module has a gateway, if you're working with a system that has a gateway connection, and you do measure pins 6 and 14 on that DLC, you may see on some cars 120 ohms of resistance, which is completely normal because that's diagnostic and terminating resistance. That will send some people for a loop or a loss because they think they have a break in the circuit when that is actually completely normal because you're only measuring CAN bus data for diagnostic CAN, which is just the DLC to the gateway. So that can be a little confusing for some people. So the best way to avoid having that confusion where you think you have a problem and you really don't is to look at the wiring diagram. If you have a gateway module, if the DLC reports directly to a gateway module, you can't measure bus resistance from the DLC. You have to go to a spot on the bus somewhere to measure it.
They have a question for. Maybe you can't exchange the gateway control module of with a program, or you have to program.
It depends on the car. A lot of them need to be
Mach-E, for example,
programmed.
Program.
That gets programmed. Now on the Mach-E, I have had okay luck putting used ones in.
All right.
That's a whole. We could do a whole other class on which cars take used modules and which ones don't. But on the Fords, I've had okay luck taking used gateway modules and putting it from one to another. You can change the VIN in there. There's not much computing that happens in the gateway. The gateway is just a guide for who gets to talk to who. And when I program it, I just say, okay, this car has this module, and this is the VIN for the car.
If you have a module from Junker installing the Mach-E, maybe go.
It usually works. You still need to program it, because the VIN will be incorrect. But you can exchange it. Yeah, most of the time, most gateways, I've had pretty good luck. Now, that is not true with a secure gateway.
It's different.
Yeah, secure gateway means Chrysler products where you can't get on the bus without a scan tool that gives us a special scan tool that gives us access to that bus.
In USA, what these scan tools go better for Chrysler?
Yeah, so which ones go better for Chrysler?
Yes.
They need to be accepted by an Authy website, a third-party provider of authorization. So AutoAuth is who we use in the United States. So I have to have a scan tool that AutoAuth, it says, is a acceptable scan tool to get in that secure gateway. And so far, pretty much everyone you can buy, TopDon, Launch, Snap-on, Autel, AutoAuth has worked well with all those.
TopDon?
Yep, TopDon.
Snap-on?
Snap-on.
Launch? Outer?
Yep, Autel.
Okay.
All the big manufacturers, for the most part, all AutoAuth accepts them. So you have to go on to AutoAuth in the United States. I register with them, say, hey, this is me. When you see this scan tool, tell the car that I'm not a criminal and allow my scan tool to talk to the car. And it just basically unlocks the gateway so that I can talk to the car. So if the vehicle has that secure gateway, that's a case where I cannot take that gateway and put it in another car. A used secure gateway does not work in another car.
It's a problem in USA that term. It's a problem in the security gateway.
Yes.
It's a big problem for a lot of shops don't understand how it works and how to get the AutoAuth to get it unlocked, so that we can communicate with it. So if you can't
if it is a secure gateway in the USA,
Yes.
we have laws that state
That when you sell a car in the United States, you have to give everybody access to emissions stuff. So if I want to talk to the engine control module for emissions, what I can do in that control module, in the engine control modules, I can read codes, I can read data, but it does not say I have to have bidirectional controls, and I don't have the ability to clear codes.
In the future, it's difficult for the mechanics.
yes. So
The secure gateway started out, as you know, with Chrysler. Nissan now has it. Ford has moved to it. Kia and Hyundai have moved to it. Everybody in the next couple of years, especially once UDS rules out, will have a secure gateway. So without being authorized to get access to that secure gateway, you're going to have a problem.
Okay, Robert, it's okay.
Yeah, thank you.
Hey, if you
Yeah.
Bueno, compañeros, antes que termine Robert, pues, bueno, aquí hay algunas preguntas que yo he realizado a Robert. Él tiene acá el tiempo bastante siempre, eh, digamos, bastante ocupadito está Robert. Entonces, le agradecemos montones. Yo bueno, está en inglés, la voy a colocar en el grupo permanentemente, la voy a colocar ahí como un video para que la vean y quizás seguramente pues pueden escucharla con más detenimiento y hacer las traducciones del caso a los que por ahí de manera rápida no lo logran hacer. Eh, no sé si tienen alguna pregunta final. Bueno, espero que hayan disfrutado la charla. Como les decía, Robert es una persona que muy experta en el tema automotriz, conoce muchísimo toda esta tecnología acá en Estados Unidos y es de los, digamos, instructores de instructores, train the trainer en Estados Unidos, Robert. Y nada, pues, thank you, Robert, from my group. Thank you for the class, excellence.
excellent. Thank you. I appreciate everybody's
Amazing,
time.
wonderful, beautiful.
I appreciate the master Teal letting me in here, take up some of his time.
Okay,
um, they want to know
where can follow to you? Facebook, I don't know.
Okay, so you can find me, Robert Kenny Jr. on Facebook. The best spot on Facebook is to go to the Automotive Technician Training Connection group, and I will let you into that group, and then you can find me through there. So I manage the Automotive Technician Training Connection group.
All right, right. All the people here, Colombia, Venezuela, Argentina,
Yeah.
in Spanish, but like Robert.
Well, thank you.
Thank you. Bueno, muchachos, muchas gracias por escucharnos. Ahí ya escucharon las redes. Yo las voy a copiar en el grupo para que las tengan. Y saludos de Córdoba, Veracruz. Bueno, saludos de Córdoba. Bueno, mucha gente acá en el grupo. Hoy entraron todos, está bueno. Está Samuel de Brasil también por acá, están todos. Entonces, nada, espero que lo hayan comprendido. Pues gracias a Robert nuevamente. Thank you, Robert. Y nos vemos, compañeros. Muchas gracias por escucharnos este ratico. Gracias por sacar el tiempo. Y nos vemos ahí en una próxima oportunidad. Chao, compañeros. Nos vemos. Muchas gracias a todos.
Saludos.
Gracias, saludos.